We are in section 1.4, Functional Models. Mathematical modeling is a method of simulating real-life situations with mathematical equations to forecast their future behaviors. Steps to mathematical modeling involve formulating a mathematical model, analyzing the model, interpreting the model, and test the model and adjust if necessary. Make sure you use common sense as you're going through these to check your answers, to make sure that it's a reasonable answer as you go through them. You also need to come up with a formula, and that's what that model is that you're going to be having. And that formula is going to take into account different aspects for the problem. All these problems are going to be different, and so you have to make sure to read the problem a few times before beginning. So the first example says Amanda wants to build a closed cylindrical water tank for her farm with a capacity of 11,000 cubic feet. The cost of the material used for the top is $3 per square foot, while the material used for the bottom and the curved sides is $5 per square foot. Express Amanda's total cost of constructing the tank as a function of its radius. So when it says as a function of its radius, this means that our solution will have r's in it. So solution has r's in it. And we'll say r is for radius. So from this, the first thing is we have a closed cylindrical water tank. And so what that is, it looks like a soda can. And so with this tank, we have a top, we have a bottom, and we have those sides that wrap around the tank. And we know that it has a total volume, and I'm going to call V equals our volume of 11,000 and cubic feet. So put feet cubed here. And with our cylindrical water tank, you can think about the top and the bottom are going to be circles. And if you were to cut open that side and lay it out flat, so if you can imagine cutting a Coke can from the bottom upwards to the top and then laying it open, you would notice that you would have a rectangle, which is what wraps around that Coke can. That's that curved side. So for this problem, we are dealing with surface area. And the area of a circle is pi r squared. And then the area of our rectangle, the part that wraps around the can, we'll call this part h for the height. And then it's going to be 2 pi r, which is the circumference of that circle, or when you open it up, that length of that side. So in order to find the volume of our cylindrical water tank, the formula is going to be V equals pi r squared h. And again, if you don't know a formula on homework, you can always email to ask or look it up online. On an exam, any formulas like this I would be giving to you. And so we know that the volume is going to be 11,000 cubic feet, which is equal to pi r squared h. And so for this problem, we know that we're only allowed to be dealing with r's and not h's. So I'm going to go ahead and solve this for h. And so this means that h would be equal to 11,000 divided by pi r squared. And so we can substitute this into the next part that we're going to talk about, which is the cost. Since it does say the top would cost $3 per square foot, and the bottom and the curved sides are $5 per square foot. And so we have to come up with the top amount that we would spend. And we'll say the top, and I'll say the dollar amount for the top, which is going to be equal to that area of the circle, which is pi r squared, times $3. So we'll say 3 pi r squared. And then the amount for the bottom, which is very similar, except for the bottom does cost $5. So this would be 5 pi r squared, since we are dealing with the area of a circle. And then the sides, since we have a rectangle here to find the area, we just have 2 pi r times h. And so for the sides, the cost, the dollar amount, is going to be 5 times 2 pi r h, or 10 pi r h. And so the total amount of money to build this can or this water tank is going to be 3 pi r squared plus 5 pi r squared plus 10 pi r h. So combining all of these parts here into a single equation, and so that's going to be 8 pi r squared plus 10 pi r h. And so our formula is only supposed to be a function of the radius as stated up above. And so I'm going to go ahead and substitute in what h is. And we know h is equal to 11,000 divided by pi r squared. So for this problem, the total amount that we would spend is going to be equal to 8 pi r squared plus 10 pi r times h, which is 11,000 divided by pi r squared. From here we can simplify this. If you notice, one of your r's would reduce, same with the pi, and then we can multiply 10 times the 11,000 and add a 0 to that 11,000, and now it's 110,000. So our total amount spent is going to be 8 pi r squared plus 110,000 divided by r. So depending on the size of water tank that she would like to build, that Amanda would like to build, that radius is going to define that size and that cost that we're going to have for this water tank for her farm. So this would be our formula. The next example says, during a drought, residents of Marin County, California, were faced with severe water shortages. To discourage excessive water usage, the county's water district initiated drastic rate increases. The monthly rate for a family of 4 was $1.22 per 100 cubic feet of water for the first 1,200 cubic feet, $10 per 100 cubic feet for the next 1,200 cubic feet, and $50 per 100 cubic feet thereafter. Express the monthly water bill for a family of 4 as a function of water used. So the first thing is there's different tiers here. So we have the first cost, which is going to be $1.22 per 100 cubic feet for the first 1,200 cubic feet of water. So the second tier of water, and then there's a third tier of water. So we're actually going to have a piecewise function that we're going to be creating here. So I'm going to go ahead and put a bracket right here, and the first one is $1.22 times x, and we'll say let x equal the cubic feet of water that you're using. So we'll say x equals cubic foot of water used. And this is only if our values are for the first 1,200 cubic feet. And I want you to note that it's $1.22 per 100 cubic feet. So this is actually for values that of x that are going to be between 0 and 12. Since this is in cubic feet, and we're also dealing with cubic feet here. So for the second cost that we have, so for our second cost, I'm going to call that C2. We're going to spend $1.22 for the first 1,200 cubic feet. So we would have that, that's the original, that first tier cost, plus the second tier, which cost more. And this one is costing $10 per 100 cubic feet for the next 12 cubic feet. So this one's of $1.22, it's now $10. And this is going to be the amount of water that you use that we would multiply it by. However, the first 12 that we had in those hundreds of cubic feet was under that first tier, so it only cost $1.22. So if you spent, let's say you use 1,500 cubic feet, we would have the first 12 for $1.22, and those last 3 would have been at the $10. So to express this, we're going to say x minus the original 12 that you had. And so if we were to simplify this, 1.22 times 12 is going to be 1464 plus 10x minus 120. And then this would simplify to 10x minus, and then we have 120 minus the 14.64 is going to be 105.36. So our second equation is going to be 10x minus 105.36. And this is if x is greater than 12 or less than or equal to 24, which would be that second set of 12 cubic feet that we would have. And then our third cost is even more. So it's going to be the $1.22 for the first 12 plus $10 times the second 12 plus $50 thereafter. And so we would say this is for any amount that you have water that you're using minus that first 2,400 cubic feet of water that you are already paying for at the tier 1 and tier 2 level. So simplifying this, we have 14.64 plus 120 plus 50x minus 1,200. And then combining our like terms, we get 50x minus 1,065.36. And so that third tier, for that, if you were into that third tier, you're going to have 50x minus 1065.36. And this is if x is greater than 24. So we have different tiers here. This is very useful to see how piecewise functions are used. In constructing mathematical models, it is important to consider proportionality relationships. The following 3 proportional equations are given for some constant value k, and a quantity q is said to be, and so we have directly proportional, inversely proportional, and jointly proportional. So directly proportional is where you would multiply a value times a constant. And inversely is where you would be able to divide by that. Jointly proportional is going to be where you have more variables, so k times x times y would be equal to q. The example right below says the rate at which an epidemic spreads through a community is jointly proportional to the number of people who have caught the disease and the number of people who have not. Express the rate as a function of the number of people who have caught the disease. And so we're going to define some variables. We're going to say where, and we're going to say x equals, and this is going to be the number of people who have had the disease. And we're going to define y as the number of people who do not have the disease. So from here we can say that it would like us to express this in terms of the people who have caught the disease. So those are the ones that have had the disease, and this is in terms of x for us, since that's what we defined our variable x to be. And so since this does say that this is jointly proportional, we know that q is equal to k times x times y. And so solving this for x, we get x is equal to q over k times y. The top of the next page, it says the law of supply and demand. It says in a competitive market environment, supply tends to equal demand, and when this occurs, the market is said to be in equilibrium. And so you can see that in the diagram to the right. We do have our supply function and our demand function. And so the equilibrium price is going to be where supply is equal to demand, and we can see that in that intersecting point. And then we have shortages if demand is greater than the supply, and a surplus if the supply is greater than the demand. So definitely things to know for our economic part of the course. The example right below this says the demand curve for a product is given by d of x equals 120,000 minus 500x, and the supply curve is given by s of x equals 1,000x for x between 0 and 120,000, where price is in dollars. Part A says at a price of $100, what quantity are consumers willing to buy and what quantity are producers willing to supply? Will the market push prices up or down? So the first thing that we need to do is to find the quantity that producers are willing to supply and that consumers are willing to buy. So our demand function that they're willing to buy would be d of 100, and substituting this into our equation up here above, we're going to have 120,000 minus 500 times 100, which works out to being 70,000. And the supply of 100, when the price is $100, is going to be equal to, and our supply function is also given to us, so this is 1,000 times x, and x in this problem is 100, and so this works out to being 100,000. And so we do have that demand, so d of 100 is less than our supply at 100. And so since our demand is less than what we have for the supply, the price should drop since we have a surplus. So we'll say price should drop because we have a surplus. So we have more of a supply than we do a demand, so that price should drop to make sure that we hit that equilibrium price. Part B says find the equilibrium price and quantity. Does your answer to Part A support observations that the market forces trend to push prices closer to the equilibrium price? So first thing is we need to find the equilibrium price, and so we find that by setting our demand equal to our supply. And so our demand function up above is 120,000 minus 500x, and that's equal to the supply, which is 1,000x. And so solving this and dividing both sides by 1,500, we get x is equal to 80. And again, this is a price, and I will go ahead and put a dollar sign on there. And so for this, we know that that equilibrium price is $80, and yes, it matches to what we have up above since it was a price of $100, and we said the price should drop in order to meet that equilibrium point. And so for this, we would say yes, it does match, but our equilibrium price is going to be $80, and it does also want our quantity. And in order to get that quantity, we just need to substitute it either into our demand or supply function that we have. And so I'm going to go ahead and substitute it to our supply since it's an easier equation. And so the supply when we're selling this for $80 is going to be 1,000 times x, which in this problem is 80. So this works out to being 80,000. And so our equilibrium quantity is equal to 80,000 units. So the example right below says if the demand curve is given by d of p equals 21 minus 3p squared, and the supply curve is given by s of p equals p squared plus p plus 3, Then find the equilibrium price and equilibrium quantity for the problem. So we are looking for both the price and the quantity that cause the equilibrium to occur. And so in order to find that price, we're going to go ahead and set D of P equal to S of P. And D of P is given up above. And this is going to be 21 minus 3P squared, which is equal to S of P, which is going to be P squared plus P plus 3. And since we're now not dealing with a linear equation, we're dealing with a quadratic equation. Remember, one side of this will need to be 0. And so I'm going to go ahead and add the 3P squared to both sides and subtract my 21. And so we're going to get 4P squared plus P minus 18 is equal to 0. I'm going to go ahead and use the guess and check method. So we do have some options here, and it might take some time in order to get this. But I know that 4 can either be 1 and 4 or 2 and 2. So I'm going to go ahead and just say P and 4P. And then also in addition, I know that in order to get 18, it can either be 18 and 1, 6 and 3, 2 and 9. So I'm going to go ahead and put a 2 and a 9 here. Looking at this, I notice that my P times 4P would be P squared. My 2 times 9 would be the 18. I do have to put my signs in. But that middle term, we would have a 9P and an 8P. And I need it to be positive 1. So I need the 9 to be positive and the 8 to be negative. From here, you can multiply this out just to make sure that it does multiply and give me the equation that is right above it. But from here, setting each of these equal to 0, we get P is equal to 2, and P is equal to negative 9 over 4. And so this is our price, and you should note that the second one is a problem. Price cannot be negative. So price can't be negative. And so we'll just go ahead and cross that one off. So our equilibrium price is going to be $2. So I'll go to make a note up above. Equilibrium price is equal to $2. And so to find that equilibrium quantity, I'm going to go ahead and substitute this into one of the equations that we have. We have demand and we have supply. This time I'm going to go ahead and substitute it into my demand since that one's a little bit easier of an equation. So 21 minus 3 times 2 squared. And this is going to work out to being 21 minus 12, which is equal to 9. And so our equilibrium demand or quantity is going to be 9 units. At the top of the next page, we have what's called a break-even point. And this is the point where the total revenue is equal to the total cost. This is the point where the manufacturer experiences neither a profit nor a loss. And so you can see this with our graph. We have our revenue and our cost. And then we have our break-even point in the middle. And that break-even point is going to be where revenue is equal to cost. And likewise, if cost is more than revenue, we experience a loss. And if revenue is greater than cost, we get a profit, which is what the company would hope for. So the next example, I'm going to go ahead and circle, and we'll look at this one together in class.